This video tutorial shows the use of the MMD program to select informative loci for source attribution. The aim of selecting informative loci is to obtain source attribution of good quality by using as few loci as possible. In order to do that, the MMD program uses concepts from information theory to provide several measures for the discriminatory power of loci. This tutorial will illustrate the use of the methods for humans from the 7 regions shown in the map. Genotypes in this dataset consist of 2,810 SNPs. The program allows us to sort the importance of loci following 3 strategies. Strategies 1 and 2 are based on the entropy within sources and between sources, respectively. Strategy 3 sorts loci in order of increasing redundancy. We normally use it to fine-tune the orderings obtained with strategies 1 and 2 to correct for redundancy. We now use the MMD program to analyze loci entropies and implement strategies 1 and 2. To do this, we set the input file as follows. We start by specifying the name of the data file and the corresponding number and names of sources. We then set to Y the switch to calculate entropies. For this example, we deactivate the switches for attribution and redundancy by setting them to N for no. At this point, we can run the program by double-clicking on Run MMD BAT file. Once the calculation has finished, the program window shows the files created in the project folder. The entropies of loci are stored in 3 files. The first file contains the list of values of the total entropy of each locus, in the order they appear in the original genotypes data file. A histogram for the total entropy is shown in page 1 of a new PDF file. In this case, there is a good proportion of loci carrying an information that is close to 1 bit. The results for entropy between sources are stored in a similar file, and the corresponding histogram is generated in page 2 of the PDF file. From the histogram, we see that loci in this dataset have a relatively low entropy between sources. Results for the entropy within sources are stored in a similar way as for the other 2 entropies. The program also generates CSV data files with loci sorted in decreasing total entropy, decreasing between source entropy corresponding to strategy 2, and decreasing within source entropy, which corresponds to strategy 1. These files contain the same data as the original data file used for the analysis, but the loci columns are sorted in a different way depending on the ordering strategy. Using these files, it is easy to do source attribution or self-attribution by targeting a selection of loci that have been identified as informative. As an example, we now use the file corresponding to entropy between sources to target loci with strategy 2 for self-attribution. We first set the relevant entries in the input file to do self-attribution, as explained in the video tutorial 2. Here, we will only use the first 100 loci in the CSV file, which have the largest between source diversity. After running the program, new files are generated, and in particular, the probability of correct self-attribution to each source is summarized in the file starting with probability correct self-attribution, which looks like this. The last row in this file gives the mean probability of correct self-attribution, which in this case is 0.63. Here, bear in mind that specific values in this file will vary a bit each time the program is run, since genotypes set as unknown for self-attribution are randomly selected each time. The plot shows the results of doing self-attribution selecting different sets of loci. One can see that selecting 100 loci with strategy 2 already gives a high probability of correct self-attribution. In this example, including the remaining 2,700 loci available in our data only improves self-attribution by 12%. The effect of selecting informative loci is even more drastic for the Campylobacter dataset used in tutorials 1 and 2. In this case, one can see that selecting around 10 loci is enough to obtain a very good self-attribution probability. The last block of this tutorial shows the use of the program to implement strategy 3 through the analysis of loci redundancy. In particular, we will refine the ordering obtained with strategy 2 to reduce the redundancy. To do this, we read the genotypes from the HL between file. We'll only consider the first 500 loci with the highest between source entropy. To analyze the redundancy of loci, we need to set the corresponding switch to Y. We now run the program, which opens a window which looks like this once the computation finishes. As usual, the results of the calculation are stored in the project folder. The analysis of redundancy is stored in 4 files. The file ending with rn original contains 2 columns. The first gives the locus number, and the second gives the redundancy of loci when they are added to the list in the order they appear in the CSV data file used for analysis. The list starts with locus number 2 because the program uses the first locus as a seed for the refinement to reduce redundancy. Therefore, locus 1 is not included in the list. The redundancy of locus 2 in this case is just the reduction of uncertainty of locus 1 when locus 2 is added to the list of selected loci. A plot of this data file is presented in Figure 1 of the PDF file generated by the program. The file ending with rn sorted presents the locus number and redundancy of loci sorted by increasing redundancy. A plot of the data in this file is shown in the PDF file with loci relabel from smaller to larger redundancy. As expected, redundancy increases monotonically in this plot. The program also generates a CSV file with genotypes following the loci ordering, which minimizes the redundancy. This file could now be used for self-attribution targeting sets of loci with small redundancy. Doing this would give the results shown by the triangles in this plot as a function of the number of targeted loci. The results will again vary a bit in each run depending on the specific genotypes chosen as unknown for self-attribution.